Hey guys! Today's video is about proximity measures for numeric attributes. I only cover normalization of numeric data in this video, and you can find the others in my channel. Numeric data is quantitative and expressed in numbers. There are two steps to calculate the dissimilarity for numeric data. We first normalize the data, then use Minkowski distance to measure the dissimilarity. Normalization is a process of adjusting values measured on different scales to a common scale. We typically use the range of 0 to 1. The reason why we need to normalize the data is to make all the attributes have equal weights. If we don't normalize the data, attributes with greater range will unfairly affect the distance measure. For example, Michael and Emily did two tests, and here are their scores. If we simply calculate the distance by deducting the lower score from the higher score, then we get the distance for test 1 is 99, for test 2 is 1000. It seems like the distance in test 2 is much larger than in test 1, but we haven't considered the range of data yet. Say the range of test 1 is 1 to 100, and the range of test 2 is 1 to 10,000. Here comes the question. Michael and Emily's scores in test 1 are actually on the two extremes of data range. However, in test 2, the difference in their scores is 1000, which is around 10% of data range. If we don't normalize the data, the distance in test 2 looks 10 times larger than in test 1. However, this result doesn't faithfully reflect how distinct the scores are, given the ranges are different. Therefore, normalization is a necessary and important step if the attributes are measured on different scales. The normalization method I want to introduce is maximum and minimum normalization, which is based on a linear transformation. It's, of course, not the only method you can use, but it's commonly used in practice. The formula goes like this. It's not a crazy math problem and it's quite straightforward. Vi prime is the data after normalization. Vi is the original data. Minimum and maximum is the original range. For instance, the range of test 1 is 1 to 100, so the minimum is 1 and the maximum is 100. New minimum and new maximum are the data range you want to transform your data to, so it's quite flexible. In most cases, we transform our data to the range of 0 to 1, so new minimum is 0, and new maximum is 1. Again, it all depends on your interest. You can convert the data to the range of -100 to 0. That's totally fine. However, if you choose the range of 0 to 1, the formula becomes surprisingly simple. New maximum minus new minimum is 0, and new minimum itself is also 0. So, what you get is new data equals to the original data minus the minimum, divided by the original data range. Let's come back to the example before. Here's the information we need to normalize the data. Say, we want to normalize Michael's score in test 2. Can you parcel out the numbers in the formula? Vi is the original data, which is 1000. Maximum and minimum are corresponding to the original data range, so minimum is 1 and maximum is 10,000. After knowing this, normalization is a snap. The score 1000 becomes 0.099 after normalization. I'm sure you can figure out the rest and just pause for a few seconds to practice by yourself before I tell you the answer. The table below is the complete normalized data. So, what have the normalization done exactly? First, the range becomes 0 to 1 for both test 1 and test 2. That is, we unify the range for all attributes. Second, by simple deduction, the distance for test 1 becomes 1, for test 2 becomes 0.1. Remember, Michael and Emily's answers are on the two extremes of the original data range in test 1. After normalization, the difference between them becomes 1, which is the maximum distance you can get in a new range of 0 to 1. Before normalization, the distance in test 2 is 1000, which is much larger than the distance in test 1. However, the difference between Michael and Emily's score should not be interpreted as strong, considering the range of test 2 is 1 to 10,000. Normalization corrects this bias by taking the range into account. Hence, the distance between Michael and Emily in test 2 is now 0.1. If you compare the distance in test 1 and test 2, you will find the distance in test 1 is much larger than in test 2 after normalization. In other words, we kind of interpolate the values into the original range to get the unbiased position of each data point in the range of 0 to 1. That's the basic idea of normalization. I'll talk about the distance measure in next video. Thank you for watching my video and I hope you enjoyed it.